So our next speaker is Jamie Haddock from Harvey Mudd College, and she's going to be talking about paving the way for consensus convergence of block gossip algorithms. Take it away.
Great, thank you, Mary, and thanks to the other co-organizers of this session. It's been really fascinating thus far, so excited. Okay, so I'm going to be talking about some recent work with an exceptional PhD candidate at UCLA, Benjamin Jarman, and a former undergraduate at UCLA, Chen Yap, who's now at Planet Labs. The work is going to discuss the average consensus problem, and I'll particularly be focused on a class of models that Gadir, the previous speaker, alluded to, the gossip method. I'll be showing you kind of a connection to numerical linear algebra via the block Kaczmarz method. And I'm going to use that connection to show you some convergence results. And maybe at the end, I'll allude to kind of a broader bridge between dynamics on networks and numerical linear algebra. Okay, so we'll talk about average consensus first. So I don't think that this slide is necessary for this group in particular, but let me just make sure we're all on the same page. So what is average consensus? So if you have an undirected graph, right here, we have our node G. We're going to imagine that there are these scalar values assigned to the nodes. So initially, there's kind of this sense of secret values. All of these nodes know their values. And the goal of the average consensus problem is for these values to be updated at each node over time, iteratively, until all of the nodes know and contain the average value, the average being the average of all of their initial values. Okay, and the challenging part here is that we want to design protocols and methods that allow only local communication on the graph. They have to respect the graph topology. All right, again, another slide that is not necessary here, but if you are thinking to yourself, what are the applications? Here's a big list of applications of average consensus. So I'll jump right into the block gossip method. Okay, so the block gossip method is a protocol for allowing the nodes to update their values. So given our graph G with initial values C naught and some set of subsets of edges T, okay, in each iteration, we're going to choose an edge subset uniformly at random from the allowable set of edge subsets. We're going to form the edge-induced subgraph of G, and then we're going to allow nodes in that edge-induced subgraph to average their values across the connected components in that edge-induced subgraph. And the nodes outside of this edge-induced subgraph do not update their secret values. Okay, and so this is how we produce the new set of values at the nodes, which will denote CK. Okay, so if we're looking at this picture, I'm going to imagine sampling the two edges connecting -17 and 0.1, and then 0.1 and 1.9. The edge-induced subgraph is just the path on those three nodes, and we allow the nodes along that path to average themselves, which averages to -5. Okay, so that's the block gossip method. We just repeat this process over and over again. There are multiple forms of block gossip methods. I'm highlighting three particular structures here. One popular protocol comes from sampling paths, one from cliques, and then one from sampling what are called edge-independent sets. And we'll come back to that. Okay, so I've introduced the block gossip method, and now I'm going to introduce the block Kaczmarz method, which you'll see very quickly why. Okay, so the block Kaczmarz method is a method for solving a linear system of equations. So if we have a measurement matrix A and the right-hand side are measurement vector B, and some initial guess at a solution X naught, and then sets of row indices from our matrix A, the block gossip method iteratively asks us to choose a row block uniformly at random from T, and then to update the previous iterate by projecting it onto the solution space of the sampled set of rows of our system. Okay, so in this picture, we have xk minus 1 gets updated to xk by projecting onto the solution space of the two rows, the kind of teal and green rows of our system. Okay, and we would just do that process over and over again, and thus get closer to the solution space of the system of equations. So one quick question. So how do we choose the subset of rows T? So one kind of way of talking about the subsets of rows that one might want to use is this concept of a row paving. So a D alpha beta row paving of a matrix A is just a partition of the row indices that satisfies that the maximum and minimum eigenvalues of the kind of Gramian of the sampled rows are bounded below by alpha and above by beta. Okay, so it's kind of giving us a control of the spectra of these subsets. Okay, so this concept has been studied in the literature. This particular definition is coming from previous work in analyzing the randomized block Kaczmarz method. Okay, but I'm going to talk very briefly about a generalization of this idea. So we're going to define a D alpha beta little r, capital R, we're running out of variables here, but a row covering of a matrix is exactly the same idea. It's still, it's still covering all of the row indices. It still gives us control of these minimum and maximum eigenvalues, but now we don't require that this is a partition, and the little r and capital R variables are going to deal with the redundancy of the appearance of the rows in these subsets. So little r is the minimum number of times that a row appears in a block, and capital R is the maximum number of times that a row appears in a block. Okay, so a couple of definitions. And what these give us is a way now of proving some nice convergence results, and I'll relate that back to the original application to average consensus. Okay, so you've seen the block-Kaczmarz method. We're going to imagine applying the block-Kaczmarz method to a least squares problem where the measurement matrix A is potentially rank deficient. Okay. We're going to imagine that we have a row covering of the rows of A, and we're going to be running block-Kaczmarz on the system defined by A and B, starting from initial iterate x naught, and we're going to kind of try to understand how quickly or really how closely these iterates get to the least squares solution. Okay, so what we can say is that the error of the jth iterate is bounded above by something that decreases linearly in expectation with the, just linearly with this kind of convergence bound, which deals all of these parameters R, beta, D, all come from the row covering. And then we have the minimum non-zero singular value of A squared. Okay, but what this second term represents is a convergence horizon, which deals with just the amount of error in our least squares problem to begin with. And again, all of these parameters come from the row covering, except for this, again, minimum non-zero singular value of A. Okay, so we have this bound, and now I'm going to be first relating it back to previous bounds in literature, and then using this to give us some understanding of the convergence of the block gossip algorithm. Okay, so if you are familiar with some of the work of Deanna Needell, or in particular, Deanna Needell and Joel Tropp's 2014 analysis of the randomized block Kaczmarz method, let me just say that the result you just saw generalizes their result in a few ways. So first, it deals with the case where the least squares problem might be rank deficient. It relaxes the requirement that the row blocks be sampled from a matrix paving to this concept of a covering. And it demonstrates that the convergence horizon depends upon the minimum non-zero singular value of the blocks rather than the absolute minimum singular value, which can often be 0. And if you're asking yourself, okay, why do you care, right? Here's a list of generalizations. What's good about that? So these generalizations are important for the application we'll see to average consensus and to the block gossip methods, but they're likely of interest in other applications where you might be trying to solve a rank-deficient least squares problems for other reasons. Okay, so the main goal now is just to apply this to the average consensus and block gossip method. So block gossip method is a special case of block Kaczmarz, where we have a particular linear algebraic formulation of the average consensus problem. So once we have that block Kaczmarz convergence result, it actually just yields as a corollary a convergence result for the block gossip method. Okay, so a reminder, if we have a graph over here on the left, then we can create a representation of that graph topology known as the incidence matrix. So the incidence matrix is a matrix in which the rows represent edges of the graph and the columns represent nodes in the graph. So in each row here, we have a 1 and a -1 indicating the 2 nodes that are connected by that edge. Okay, and the positioning of the 1 and the -1 for our situation at least it does not matter. You can swap them. And now the idea is just that the block gossip method with some edge subset blocks T produces exactly the same iterates as the block Kaczmarz method if we run the block Kaczmarz method on the linear system defined by the incidence matrix and right-hand side 0, and starting from initial iterate being the initial secret values of the nodes. Okay, provided we use the same row blocks as the edge sets in T. All right, so like I said, we just immediately get as a corollary this result. So suppose we have a connected graph, right? We've got our incidence matrix Q, and we have a set of row coverings for Q, or sorry, a set of subsets forming a row covering for Q. Here, M is the maximum size of any of the row subsets. When we run the block gossip method with blocks determined by T, this is going to converge at least linearly in expectation. So in expectation, the norm of the secret values minus C star. C star here is the constant vector where all of the entries are equal to the average of the entries of C naught, the initial secret values, right? That's the solution to the average consensus problem. So that norm squared is going down according to this rate parameter, 1 minus R alpha of G over beta times D. So R, beta, and D all come from the row covering. Alpha of G is the algebraic connectivity of the graph, or the minimum non-zero singular value of the incidence matrix. Okay, so that's the result. Let me just say there's some special cases that apply to the 3 particular protocols, gossip protocols I mentioned before. So we can specialize this rate constant, and particularly just we can deal with the kind of question parameter, which is beta. So if the row subsets that we're sampling or the edge subsets that we're sampling represent independent edge sets, then this rate constant can be bounded above. We can replace beta with the value 2. If our samples correspond to cliques or paths, then the rate constant can be bounded above by this kind of surprising value to me, 2 minus 2 cosine m pi over m plus 1. But in particular, you can always bound that above by 4. And then in general, if we have just any arbitrary connected subgraphs, we can bound it above by the maximal size of any of those subgraphs that we're allowed to sample. Okay, so that's the convergence result. Let me briefly comment on some future work. So it's well known that there's a natural bridge between many problems regarding consensus dynamics on networks and classical iterative methods from numerical linear algebra. But in particular, I'm hoping to kind of further use this bridge to kind of deal with more complex models coming from dynamics over networks. So, this could be distributed consensus. There's many relevant models in opinion dynamics coming from ranking models, or just generally, there's a lot of reasons to be interested in Laplacian systems, even just for general linear solvers. All right, so with that, let me just conclude, remind you of my wonderful collaborators, and remind you that what we've seen today is that the average consensus problem, we may formulate it as a least squares problem. We can then view possible popular gossip methods as special cases of Kaczmarz methods, or possibly other classical methods from iterative linear algebra. Convergence results for those numerical linear algebra methods then provide us corollaries, convergence results for the gossip methods. And my hope is that this technique may be exploited for other consensus dynamics problems on networks. All right, with that, I will wrap up, and I thank you for your attention.
Thanks so much. We have time for a quick question if anyone has one.
Hey, can I ask a quick question?
Yeah.
Thanks, this is cool. So the pavings that you're talking about usually, is the idea to design this, or it's just a tool to study it when it exists?
Yeah, that's a great question. So I'd like to say a little bit of both. Right now, it's probably the second. It's more just a tool that we were able to use to really hone in on the convergence rate. But eventually, I'd like to look at if you understand in particular your graph topology, and you have some hope that some of these convergence rates might be, I won't go as far as saying type, but representative of the convergence. Can you then design the subsamples, like a particular protocol for gossip, based on trying to optimize all of those parameters coming from the row covering or row pavings?
Got it. And then one more question in that vein, which maybe you know the answer to, but if you chose the row pavings randomly, do you have a sense of whether that could be optimal always, or if there are cases you even know about already where that's not a good idea?
So is your question whether random subset sampling is optimal with regards to all of the possible?
Yeah, can you get the optimal values of alpha and beta by doing random sampling of it?
That's a great question. So I don't know. I doubt that random sampling in particular would be optimal for those values, simply because if you're allowing random sampling, you're kind of maximizing, for sure, you're maximizing the size of D. You're allowing every possible subset to be a possible element of your sample. So I suspect that would not be optimal, but I don't have anything more than suspicion.
Or I don't know, or maybe a randomized thing where you bound maybe you bound a few things about the incidence, but that seems cool. Thanks.
That's a great question. I haven't, if you imagine random samplings of a particular size, even I haven't thought about analyzing. I mean, you can analyze R and little r and capital R easily,
right?
But beta and alpha, I'd have to think a little bit.
Okay, so I think in the interest of time, we can take other questions offline.